Hey everyone, welcome to Insights by Rish. Today we are going to implement breast cancer detection project. Now this is a binary classification project and you can implement it with various machine learning classification algorithms like logistic regression, naive Bayes, support vector machines, etc. But today we are going to implement this particular using the TensorFlow as well as Keras, which is a deep learning method. And also we are going to import the dataset of breast cancer from the sklearn library itself. Now sklearn library have many inbuilt dataset and we are going to use one of that, which is the breast cancer. So let's start. From sklearn.datasets, we are going to import the load breast cancer. Okay, let's run this. Now the next thing that we want to do, here we have imported the dataset. We want to store it into some variable which is df, and we will just load that. Now after this, the next thing that we want to do is, let us check what all contents it have. We don't have a data frame as of now. We first need to check what the contents it holds and then we can create data frame out of it. So for that, we will write dir of df and let us check. So the df variable now holds the data, the feature names, which are your column names, your target and the target names. So out of this features or out of this elements, we need to create the data frame from this. So let's say the input data frame is labeled as capital X, and we will import the pandas first. We will import pandas as PD, and in the X variable we will, which will be of data frame data structure. Into that we will create a data frame, and we are going to load the data from this. The data actually holds the original values of all the measurements. And the next thing is, now that we have data, we also need to give column names to that particular data respectively. And for that, we will provide the columns attribute into which we will provide the feature names. Now let's run this. Let us check the first 5 rows using the head method. So this is the data set that we have. We have total 30 columns. And currently we don't have the target feature into this particular data set because here, as you know, the target and the data, the actual data and the target are two separate elements in this particular inbuilt data set. So we need to load the target data as well into some different variable. As of now, this input data have 30 columns. Let us check the shape. And it have total 569 rows and 30 columns. We will also load the target data into a particular variable, let's say y, and we are also loading it into the data frame data structure, which is not a series. Generally, when you are performing machine learning and you are setting a target feature, in that case you set it to a series data structure, but here we are going to create it as a data frame data structure. So into the target we have our target data, and here we need to manually give the name of column, which will be, let us say, breast cancer status. What's the status? Like whether the patient is having it, so it's 1, or whether the person is not having it, like 0. So let us run this and we'll again display the first 5 rows. So you can see this is our target column now. This is our target feature, breast cancer status, and these 2 data frames are now separate and individual. They are not integrated. The next thing that we can do, looking at the data, I feel that most of the columns are scaled, but there are few columns which require data normalization. So let us check that first. Let us use the describe method. And what's the issue here? Okay, so the input column is X. Okay, so this is the statistical analysis of the data set, and one thing that you can see here, not all data is scaled. There are some like after the first 4 columns the data is scaled, but before that every column is on a different scale. So the next thing that we want to do on this is min-max scaling, which is used for data normalization, and we are going to import that module from the sklearn library. So sklearn.preprocessing, and we will import the min-max scaler. Now min-max scaler generally scales the data between 0 to 1. So we will create an object of min-max scaler and we'll load that library or the module. Now we will fit the data set. What we'll do, we will use the fit transform method for that. So we will write scaler dot fit underscore transform. So we are doing both the things in a single go. Now let us display the first 5 rows again from the X. Now you can see generally all the columns are scaled. So this is what we wanted. And apart from this, it won't hold any null values because this data is an inbuilt from sklearn library. So the majority of data processing won't be required here. Of course, you download the dataset if from any external sources, then you need to perform a lot of data cleaning and data pre-processing. But as this data was from the inbuilt library of sklearn, we won't require much data pre-processing and data cleaning here. Now that we have scaled the data, the next thing that we are going to do, we will perform the train test split. So from sklearn.model selection, we will import the train test split method. And now we will split it using the xtrain, xtest, and then the ytrain and ytest. So we will write the train test method, train test split. We will provide the input data frame, which is X, and the target data frame, which is Y. Then we will give the test size as well, which will be 0.2, that is the 80% data in the training set and 20% data in the testing set. We will also provide the random state, which will you can give any value particularly. That's just because when you rerun the code, you want the same number of rows and actually the same rows or same instances in the training set as well as in the testing set. So let's run this. Okay, so there's some error. I think, yeah, it's train test. It was just a misspelling. Okay, now let us check the shape of xtrain. Sorry. The shape here is 455 rows, and let us also check the shape of xtest. So you can see out of, I think we initially had 569 rows, and out of that now 455 rows are in the training set and 114 rows are in the testing set. Now the train test split has been performed. The next thing that we will do, now we will start training our deep learning model. So this is a basic neural network. Actually, we are using the artificial neural network method here. This is not a very complex model that we need to provide n number of hidden layers here. 1 or 2 hidden layers will be enough. So first we will import the necessary libraries. So import TensorFlow STF. And the next is from the TensorFlow we will import Keras. Let's run this. It will take some time because these libraries are heavy. Now we will create a model which will say Keras sequential. And S should be capital. And next we will give the input layer. First we will just try to build the model using no hidden layers. We will just have one input layer and one output layer, and then we will try with some hidden layers as well. So Keras dot layers dot dense. Dense means basically we want that every input neuron should be connected to every other output neuron, and if you don't want dense, you can try different methods as well. We want fully connected neural network architecture, hence we are using the dense method. Now see, this is a binary classification problem. The output neuron will either be 0 or 1. That means in output layer you just require one neuron which will either provide the output as 0 or 1. So hence the output neuron in the output layer would just be 1. Let us give the input shape. And the input shape would be the number of inputs that we have. So you can see in the input data frame we have 30 columns, which means we are having 30 input. So 30, and we will also provide the activation function. So this is the activation function, and we aren't using any hidden layer here. So this would be a basic perceptron, single layer perceptron model. Let's run this. Now we will compile this to model.compile. We will provide the optimizer, and currently the best optimizer that we have in any neural network is the ADAM. You can try it with stochastic gradient descent or minimax gradient descent as well. But the best one again is ADAM, because the ADAM optimizer actually smoothens your curve to reach the global minima, as well as it gives you the adaptive learning rate. So it have both the advantages that is basically present in adaptive gradient and the RMS prop. Secondly, we will specify the loss function. Now as this is a binary classification problem, we will have the binary cross entropy loss function here, which is your logistic loss function that you basically use in logistic regression. So binary cross entropy, and the last thing that we are going to give here is a matrix, and we want to evaluate this model on the basis of accuracy. So our matrix will be accuracy. Let's run this. Now we will fit. So in the fit method we are going to provide the x train, y train, and the number of epochs that we want. Now you can generally increase the number of epochs that you want depending upon the complexity of your model. I am going to give the number of epochs as 500 because that's the value of epochs I have achieved using the trial and error basis. So let's run this. Now it's fitted. It takes some time, of course. Now we will check the loss and accuracy. So here itself you are able to see that the accuracy is around 95% and the loss is around some, it would be somewhere 5%, 4%, something like this. But we'll again check it explicitly. So we will use the model.evaluate method, and in that we will evaluate the test model, the test set. Let us run this, and then we will print the loss and accuracy. So let us print the loss. We'll multiply it by 100 because we want the loss and accuracy in percent. So you can see the accuracy is around 96%, which is good. Now this accuracy here you can see, which is 95%, was on the validation set, and this 96% accuracy is now on the testing set, which is a good accuracy. Let us see some predictions. So let us display the first 5 original values, original target values, which are stored in y-test, and you can see for the first row they are saying the patient has the breast cancer, and for the next 2 patients they are saying the patient doesn't have any breast cancer, and again for the last 2 patients they are saying that the patient has breast cancer. So let us check what our model has predicted. Let us store that prediction in pred variable. And now we will display the first 5 rows of our predicted values as well. So you can see now currently the values are in probabilistic approach, or you can say the probability way between 0 to 1. and that is because we are using the sigmoid activation function. As we are having binary classification, we have used the sigmoid activation function, which generally gives you value between 0 to 1. If you want the value perfectly either 0 or 1, then you can go for the binary step function as well. But as we are using sigmoid function, we need to explicitly convert these values into either 0 or 1 depending upon a provided threshold, and let us provide the threshold of 0.5, which means any value greater than 0.5 would be considered as 1 and any value lower than 0.5 would be considered as 0. So for that, we'll store that binary predictions in a binary pred variable, and let us say that our pred should be greater than 0.5, and we'll explicitly provide the data type as well, which is int. Let us run this, and now we will display the first 5 rows of binary pred variables. Okay, so here you can see the values of the predicted values are nearly equal to what we have in the actual values. You can see the first and the fourth and fifth row consist of 1, and similarly in the predicted values as well, first, fourth and fifth rows consist of 1. Apart from that, the second and third row consist of 0, which means the predictions are good because our model is giving 96% accuracy. Now the next thing that we are going to do, here we just tried it on the, wait, let me show you, using a simple single layer perceptron. We can try adding some hidden layers and do some analysis as well. Let us try adding the hidden layers. We will add it here itself. So consider that we will add one more layer before this. Keras dot layers dot dense, and now the output would be 32. Why 32? Because you can give any number of output neurons you want. That is, this is basically the number of neurons in your first hidden layer. You can give it anything. The input neurons, or you can say the input shape, is 30. Let me copy it from here and let me paste it here. So the input shape is 30. That is, we are having 30 rows in our input data set, and the first hidden layer can contain n number of hidden neurons. We are saying that we want, in our hidden layer, we want 32 neurons in the first hidden layer. And let us provide the first hidden layer with the ReLU activation function. Basically, all hidden layers in a binary classification have ReLU activation function, and the output layer has sigmoid activation function. So let us write activation is equal to ReLU, which is the rectified linear unit, and it chooses between the maximum value of 0 or the provided x. Now this was our first hidden layer. We can add one more hidden layer, the second hidden layer that we want to add, and let's say now in the second hidden layer we want 16 hidden neurons. Now we don't require the input shape here, we just require the input shape in the first layer, that in the layer which where we are actually taking the inputs from the data set. Again, this will have ReLU activation function because this is a hidden layer, and we can provide one more hidden layer if we want. Let's say it will have 8 hidden neurons, and it will again have ReLU activation function, and this is the last one is our output layer, which has sigmoid activation function, and the output would be just a single neuron that will produce the output of either 0 or 1. Let's run this, and we'll again compile it, and we'll again test the epochs. So it will take some time. Okay, now we'll again evaluate the model. You can see first, when we didn't have any hidden layer, in that case our accuracy was 96%. Now we will test it again. And you can see even after adding the hidden layers, the accuracy is still 96%. You can say the accuracy for validation set is 100%, but for testing set it is 96%. 96% is not bad, but the reason that the accuracy remains same even after adding the hidden layers is because this is not a complex model. Accuracy only improves or depends upon the number of hidden layers when the model is complex and the model requires a lot of learning process and backpropagation process. But here the model was very simple because this is basically a basic machine learning model which we are implementing using the deep learning approach, and hence even after adding the hidden layers the number of the accuracy remains same. So I think we are done with this. We also did the predictions, and let us see, the predictions also remain same. So as the model was simple, the adding of hidden layers didn't made any difference. That's it for the video. Thanks for watching.